Okay, I think we should start. So we're really fortunate to have Misha Lukin here, who's going to tell us about quantum advantage in error-corrected computing.
I'd like to start by joining others, by thanking the organizers for putting together this very nice meeting and for invitation. So I kind of will start with the high-level slide, So this will be a talk about building, actually, quantum computers. And in doing that, we are actually forced to confront and bridge two contradictory forces of nature. So one is a kind of force of controllability, in that we really need to, control our operations, both single qubit and entangling operations on individual qubits, and then kind of, increase the system size, kind of scale the system while, maintaining this control. So, while Scott now is, trying to fight disinformation and fake news, we are still kind of at it fighting this two, kind of seemingly irreconcilable forces of nature. So, and kind of the current frontier is, the subject of this session, that we want to do task beyond modern classical computers, hopefully with over 100 good qubits, and then use this kind of experiments to figure out how to build bigger and better quantum machines, but now also starting to explore algorithms and maybe scientific applications towards what I would call useful quantum advantage. And I think that's, the real frontier, in my view, of this field. And so the kind of era we are now is that we have machines which are big enough, programmable enough, and actually quantum enough that we could really experiment with them. And it's kind of like an era of quantum discovery, if you want. So I will kind of talk today mostly about building quantum computers, but since this is an audience of computer scientists and algorithm builders, I want to kind of emphasize that the common theme of many things which I will talk about is this idea of co-design. So we would like to kind of start with some, goal, with some maybe application, if you want, in mind, build an algorithm, and then kind of find the hardware efficient implementation. And so that's kind of this interplay between these two directions is actually central to, most of what I will talk about today. So as a specific focus, I will talk today about building quantum computers using isolated neutral atoms. So you've heard already some talks about it by Manuel and I think Sun Won a little bit. So as you probably have heard, we are trapping these atoms in optical tweezers, kind of one atom at a time. And usually when we start doing these experiments, we try to now trap thousands of these atoms. We cannot trap them perfectly. So basically, some traps are empty. So the system has entropy. So and we remove this entropy literally by taking a picture and then figuring out which traps are full and which are empty, and then basically kind of rearranging the atoms in desired configuration. These moving atoms will be a key feature of my talk. So typically when we position these atoms, they are separated by a couple of micrometers. They don't interact. So to make them interact, we excite them into the state with high principal number. This is a so-called Rydberg state. And this actually is a kind of idea behind many of these experiments. And actually, our effort is a joint effort, which we started about 10 years ago with Markus Greiner and Vlad Vuletic, my colleagues, respectively, at Harvard and MIT. So just one, kind of slide, kind of overview of this Rydberg interaction. So we like Rydberg states because they have long lifetimes and they have very strong interactions. So for example, van der Waal interaction for the atom with n equals 100 is 14 orders of magnitude larger than the van der Waal interaction between ground state atoms. And also the Rydberg atoms have pretty good coherence times, kind of they can maintain coherence for hundreds of microseconds. And so we can use this strong interaction, to put this strong interaction to a very good use. So one idea how to use it is this idea of Rydberg blockade, which kind of is as follows. So suppose you have two atoms which sit far away and you drive them resonantly. So if they are very far away, they would just undergo independent Rabi oscillations. But if you bring them close, eventually this interaction will take over. And at some point, it will become so strong that basically you will not be able, with the resonant laser pulse, we will not be able to excite both of these atoms simultaneously. We can excite one or another, but never both. So that's the idea of this Rydberg blockade. And we like this approach to entangle atoms because it's very robust. It's insensitive to motion, to the position of the atom. And so in some way, it makes this interaction between these atoms digital. It's either off, or on. And when it's on, it's sort of basically, if you want, infinity. So we could utilize this effect to actually effectively sort of digitize and parallelize our entangling operations. So with all of this, so the general approach will be that we will kind of start with some atoms. In general, you will see now in two dimensions, and then we'll assemble these registers, and then we will manipulate atoms with laser pulses, change the internal states, and then eventually we'll make a projective readout, detect atoms in one state, and this will be the kind of the sequence, the experimental sequence, the quantum, computing or quantum simulation sequence. So this is now a very exciting frontier with many groups exploring different types of atoms, molecules, different types of modalities. You've heard a little bit, from Adam, I guess, the work with in Manuel's group. So one can make some now very fancy systems, for example, with 2 species. And actually, in Manuel's group, for example, is a picture of over 5,000 atoms trapped, under the microscope. So we really have numbers to work with. And so this is now basically kind of, the system is being explored in many directions. Quantum computing is one of them, quantum simulations is another, but people are also thinking about it for things like meteorology and so on. So this really basically touches almost all areas of quantum. So in our lab, we are now operating a 3rd generation of the atom array, and kind of the basic elements of this is this device called special light modulator. It's basically a computer-generated hologram, which can create basically almost arbitrary pattern in 2 dimensions of laser spots, which we project into the vacuum chamber. And this is actually an amazing device, but has one drawback: it's slow. So basically, to move atoms around, what we do, we actually have this 2nd channel, where we have 2 acousto-optic deflectors, where we basically can move, columns and rows atoms independently. And with that, we can now trap, thousands of atoms, and we can make defect-free arrays of, actually, more than 500. So kind of using the system, it's been a lot of fun. So we're basically exploring different approaches. So in a kind of quantum simulation front, we're exploring different phase diagrams, topological physics, dynamics of the system. I will mention a bit more about that. So these are all kind of, if you want, analog approaches. But we're also now exploring a digital processor, and also kind of utilizing ideas of error correction, which will be a focus of my talk. But maybe kind of upon kind of discussion with the organizers, maybe I want to kind of take a step back. So if you want, for example, to really think about how these systems can be used for quantum advantage, there are actually several avenues, and they're kind of, to begin with, don't really look very much, at least in spirit, they're kind of different, So one of them is to really explore analog dynamics. I guess you've heard about it already from Sunwon and Adam. But, one can also think about, okay, now let's combine this analog with digital. So this is a kind of, another route. And then eventually one could think about encoded qubits and quantum error correction techniques. So I think all of these things really have some distinction, but there is some kind of commonality, which actually I would like to kind of, emphasize here. And so one kind of just example, which I want to flash only very briefly, is that already in an analog dynamics, you can use, for example, techniques like Floquet engineering. And so if you just encode qubits in ground and Rydberg states, these dynamics of these qubits, and subject to the blockade constraint, is described by something like which is called PXP model. So what it really means here is that basically you can flip the qubit resonantly, apply an X operation, or if and only if its neighbors, or the qubits it's connected to, are in a kind of in a ground state. It's projected to, P means projection to the ground state. And so that's a model which, for example, underlines a lot, which you've heard, I guess, on Tuesday, the dynamic studied, for example, in Manuel's lab. But, then, of course, you can also have a laser detuning here. It's like a sigma z term, basically. And we know now already since some time, if you start kind of changing this detuning in time, you can actually enable some very cool kind of different new capabilities. And so one of them is that you can actually, by just imprinting the phase pi on this wave function, because this Hamiltonian PXP model is so-called particle Hall symmetric, you can basically time reverse the evolution, right? And you can start with dynamics, you can apply this, imprint this phase, and then basically, bring the state back. But actually, it turns out that if you start kind of tinkering with this time reversal protocol, if in addition to this, perfect time reversal, which basically changes your PXP to minus PXP, you start adding some phases during the evolution process, you can actually, do some very cool things. So in particular, what you can do, you can engineer the so-called Floquet dynamics. So if you apply it periodically, you have kind of new Hamiltonian, and kind of this ingredient of this new Hamiltonian is this, described by this kind of time evolution. So it's basically, what it does here, it kind of like it probes this kind of operator spreading during this evolution, and in fact, it results in the new Hamiltonian, which can have multi-particle interaction. So, for example, there was some talks today about, simulating lattice gauge theory. So one of the kind of critical ingredients in lattice gauge theory is so-called ring exchange term. So it's a kind of a gauge term. And actually, it turns out you can use this kind of approach to actually, kind of generate this term, which actually basically flips you between these two configurations. So red is a Rydberg atom, and white is a ground state atom. So this, the way how it does it, basically, like it, creates some kind of funny dynamics, but basically after the one period, it just does precisely, it takes you from this state to this state, and actually does so very quickly. So, and this actually kind of immediately creates a lot of cool opportunities. So for example, so this actually is first experiments where we tried. So you see that we apply this kind of very non-trivial detuning profile, but what it does experimentally is basically starting from this hexagonal lattice, it's just really, very quickly on a time scale comparable to a single Rabi flop, basically flips you from one configuration to another. And in fact, in this case, you can generate this so-called gauge field, this multi-particle hop, which is on the same time scale as a single particle hop. And you can, for example, use it to stabilize this kind of superposition states, the so-called resonating valence bond state, and it could really be an ingredient for example, to build this kind of lattice gauge theories simulation. So here is just purely analog means, and I think it's also related to some kind of new classes of Hamiltonian algorithms people are thinking about. So I think this is actually very kind of interesting kind of native, hardware possibilities. Okay, so the focus of my talk today, Wolf, will be digital processing. So where we will actually encode qubits in a long-lived states and hyperfine states, like very similar to what we've heard, in the previous talk with ions by Mikhail. And in our case, to entangle atoms, what we'll do, we'll just briefly excite them into these Rydberg states. And one of the things which actually kind of also, kind of changed the field quite a bit is our realization, a couple of years ago, that not only you can store qubits here in this long-lived hyperfine states for a long time, for like seconds, you can also move tweezers while qubits are stored without disturbing these qubits. And this gives rise to this kind of reconfigurable architecture idea, where basically the connectivity of your processor can be a living organism. It can basically change during the computation time itself, and it's actually very cool. It kind of really brings new capabilities. So in particular, one of the capabilities is non-local connectivity. So it's a little bit similar to what ions have, but in particular, what it brings, is this idea that one can very efficiently control many physical and many logical qubits in parallel. So this is what I would like to kind of now describe a little bit. So basically, this kind of, there are many new opportunities to this reconfigurable architecture. So one is that one can now combine this analog and digital dynamics. You can, for example, do some analog dynamics, then stop it, then reconfigure it, do some gates, proceed with that. So for example, we used it to measure entanglement entropy at the physical of the physical qubits. So one can also start, adding kind of new tools to many-body physics. So Susanna talked about how one could simulate some very complex non-local models, for example, for quantum chemistry. Naturally, there is also a connection to lattice gauge theories. And in fact, we even thought about sort of some approaches to use kind of mirror type constructions to simulate ADS-CFT. So it's kind of a little bit, out there. So, but actually, so just one illustration, this is a very simple circuit that, we already kind of, tried experimentally. So in which we basically alternate the 2 qubit gates and single qubit gates to simulate, in this case, 1D kind of Ising, kicked Ising model. So basically in this circuit, you have, 2 terms, non-commuting terms. One is Z and one is X. And, one can actually implement it, just by moving atoms around. So basically the idea is that you start with atoms which are separated, which do not interact. You can rotate them individually, then you bring them together, do entangling gate, then separate again, then bring them together, and you proceed to build this kind of circuit. And basically using that, for example, in this case, there is a kind of, phase diagram here for this kicked Ising model where you have paramagnetic phase and ferromagnetic phase. One can readily, for example, see, that if you quench across a phase transition, you see a different behavior. And when on one case you have non-zero magnetization, in the other case it goes to 0. So it's just a simple example. Similar experiments have been done, I think, both on ions and superconducting qubits, but now we have this possibility to really do things non-locally, right? And basically, connect things in a very, complicated and non-local way. So I think this is all like super promising, but eventually the key challenge will be controlling errors. And, that I think is a challenge all of these platforms basically are facing now. In fact, now we can have more qubits and do more gate operators than gate operations that is sort of useful because of errors. And in principle, we know since, nearly 30 years, not quite, but that there is a way to circumvent this. And this is to use basically quantum error correction techniques. Kind of basically the idea is that you use redundancy and use entanglement to encode qubits non-locally. And then you can use, for example, stabilizers to detect the errors. And in this way, basically by delocalizing, logical degrees of freedom become hard to accidentally manipulate. Of course, the caveat of that is that, they're also hard to manipulate, intentionally, right? So that's a little bit of a contradiction. But using this reconfigurable atom arrays is a very natural approach, to implement these quantum error correcting codes. And actually, some examples already relatively old. Just 2 years ago, we prepared this kind of toric code, state on a torus in this case. You would say, well, 2D with 2D platform, this torus is kind of hard to implement. But if you use atoms, is not, the geometry is no longer basically kind of well defined, And so, so this is, kind of a simple move in which we use some data qubits and some moving ancillas to basically make first local stabilizer measurement, and then we move it all the way across to basically close this kind of close this torus. So the details here are not important, but what is important? So in this case, we actually encode 2 logical qubits because it's on a torus. You can encode 1 qubit going one way and another way. But we actually, to do it, we just use 2 voltages, right? And 1 voltage moves atoms up and down, and 1 left and right. So basically, that indicates that this kind of that is reconfigurable architecture, at least in terms of efficiency of control of a logical qubit, is very, very special. So, okay, so to kind of utilize this, yeah.
Maybe I'm missing something, but wouldn't you expect the 2 logical operators to be C and X?
Yes. So in the toric code, you have basically, for 1 qubit, you have product of X's and product of Z's around, and then and product of Z's and product of X's. These are 2 logical qubits. Right? So surface code you can code 1, but here because of topology, you can code 2. And you can sort of verify that. And this case, we just prepare the state, Okay, so to take advantage of these, kind of ideas, last year we have done quite a bit of work by kind of upgrading our system. So one of them was to actually increase our 2-qubit gate fidelities, which are now maybe, second only to Quantinum. So I think our gate errors is a factor of 2. So, but we have a lot more qubits, and moreover, and moreover, we have this kind of, amazing possibility of doing things in parallel. So, for example, here we can individually address atoms, with single qubit gates. And what we do it in parallel, and we just do it by using these 2 acoust-optic deflectors. We just shine pattern of light beams on certain atoms. In this case, for example, we do Raman rotations of hyperfine of qubits. And also by using this reconfigurable architecture, it's actually easy for us to do mid-circuit readout. So what we can do, we can just take some atoms, move them in a separate zone, and just image them, while the others are preserved. So basically combining all of these elements, we kind of put together, what we thought is a kind of a logical quantum processor, which has also zone structure, but it kind of in some way it starts already looking like a computer, maybe, and it has some storage zone, some, kind of ancillary reservoir, some zone where we do gate operations, entangling operations, all done in parallel here. And then we also have kind of a readout zone. So the key ingredient of this is the shift from controlling over individual physical qubits to controlling, over individual logical qubits. And so the idea here, it can be illustrated by using the 2-qubit gate operation. So suppose you start with 2 encoded qubits, maybe 2 surface codes. So here, in both of these cases, the quantum information is stored non-locally. So to make this, gate between these 2 surface code, in general, what you need to do, you need to somehow enable some non-local, kind of, if you want, interaction between sort of each qubit here on the right, or each qubit here or on the left. So if you want to think about it in terms of anyons, you want to basically braid one anyon around another, And this typically is actually a very costly operation if you have local connectivity. So in particular, it requires many steps of error correction proportional to code distance, to lead dimension of this code. However, since many years, thanks to, in particular, pioneering work by people like Peter, so we know that there is another way of doing that. And these are the so-called transversal gates. And in these transversal gates, what you do, you basically just do parallel synods between pairs of qubits in each of these 2 blocks. So in our case, the way how we can do it, we can just bring these 2 codes on the top of each other and just basically do a synod on each pair of atoms and then kind of separate them. So this implements a logical synod. And it turns out that this logical synod has actually really quite remarkable properties. So first off, it's inherently fault tolerant, because basically errors cannot spread within each block. So actually, as a result, you might not need to do all of these D rounds of error correction. So you might get away from fewer rounds. So moreover, now this is, these operations can be completely non-local. So you can basically couple any of these 2 qubits with each other. And, this is actually a lot of that is actually, if you read carefully Peter's paper, he exactly tells us we should be doing that. So maybe a new innovation here is that we can really now think about each of these blocks as kind of 2 macro atoms. So we can think about it as 2 kind of gigantic atoms, which we can really, control with given, sort of set of laser spots. So basically, and the idea is that essentially, each, kind of physical qubits inside the block receive the same instructions, and that's for this reason this big block acts just as 1 big atom. So, so some examples of how this can be utilized. So one first example is a logical synod with the surface code. So what we do here, we prepare 2 surface codes. initialize one in X state and another one in a 0 state. So this can be done by just measuring corresponding stabilizers. And then what we'll do is we basically will do CNOT between them, basically bring them together, entangle them and take them apart and then just measure them. And so this is the smallest kind of viable. This is distance 3, but we can actually go to distance 5 or actually distance 7. And if we do this experiment, first of all, we find that this distance 7 surface codes here are entangled. And moreover, what's most important is that if we kind of do decoding properly, and I will elaborate on that, if we increase the code distance, basically our error, basically decreases as redundancy is increased. So this is a key property of the quantum error correcting code. So there are wide variety of caveats of these results. So first off, here we just do one round, one gate, and actually one round of the error correction. And in fact, because of that, it is very important to decode these errors here properly. So we actually decode them jointly. We do a correlated decoding. So if you do uncorrelated conventional decoding, the errors get worse. And also kind of the threshold for this circuit, because it's just kind of one gate, one round, is relatively high. But nevertheless, this both illustrates the key property of the quantum error correction. So basically that the quality improves with the code distance, but also it kind of shows you that already here we start learning, for example, decoding these things properly is very important, right? So okay, so that's one example. So the other thing which we could do is we could use color code. So in this example which I just described, our state preparation technically was not fault tolerant. So we can actually do fault tolerant state preparation by just taking two color codes, preparing them non-fault tolerantly, and then using this so-called steam error correction, basically using one of these encoded qubits as a kind of ancilla to basically, test, for the kind of if the other one was prepared in the right state. So the idea here is that you rotate it into the plus state, bring them together, entangle, and then take them apart and basically measure one of these qubits. So if you found that this one is 0, so then it's actually guarantees that this upper one should be 0. So, and using this kind of approach, we are able to, for example, achieve some first, break-even results. So in this case, we can, for example, prepare our logical qubits better than our physical spam. And while experiments like this have been done, most notably in a very nice paper by Continuum 2 years ago. So we have a luxury of, we don't just, of not working just with one or two logical qubits, but we can work with many. So in fact, we, did this experiment with up to 60 logical qubits. But so I will just show you an example with 4. So we, in this case, with 4 pairs, with 8, so here we basically prepare, fault tolerantly 4 logical qubits in a 0 state, and then we can use this, qubits to basically do some kind of code. So in this case, what we did, we basically prepared a GAG state. We now then do again transversal gates to entangle them, and once we have a GAG state, we measure these qubits, and what one can see is that again you can do it non-fault tolerantly, you can do it fault tolerantly, you can then also start playing with error correction or error detection. So basically, each error correcting code is also error detecting code. And so here, if you do error detection, you basically get nearly perfect. So this experiment also kind of already gives us a little bit of a hint that, like logical qubits are very different beasts. So usually physical qubits, what you do parity oscillations. This is not possible with logical qubits because guess what? They're all digital, right? So, but for that, for example, you can do measurement of all kind of logical in all logical basis. So you can do basically quantum state tomography. So basically, what you see here is that you can start really thinking about doing circuits with logical qubits. So this is the last part of my talk. So kind of we are now entering this kind of era where one can, maybe you could call it early fault-tolerant, quantum computation, where you can start thinking about, building and testing logical processors in the lab. And so I already told you that these algorithms and hardware capabilities are very important to co-design together. Now you have extra elements. For example, you need to find the best error-correcting code, which would help you to realize your algorithm. But more importantly, you now also have to think how to decode these algorithms and also how to compile these algorithms. All of that, has to be done together. And I would say next 5 years, this co-design approach will be absolutely essential to move frontier of the field. Just one example here is implementation of non-Clifford operations. So far, all what I have done was basically utilizing 2D codes, and for 2D codes, transversal gates are all Clifford, so they can be all simulated very efficiently. So if we want to go beyond, we need to inject magic, and this is, of course, the topic, of active research. You can think about injecting, magic factory, or you do some kind of code switching. So the example we have, kind of zeroed in here is the idea that if you utilize 3D codes, then you can have transversal non-Clifford operations. And this, is based on the work of several people, including in particular Alex, who is here. And kind of the code which we will use is this 832 code, is a 3D color code, which you basically can visualize as qubits sitting on the kind of at the, what do you call it? Not edges, but cube, and then you can define, stabilizers and kind of gate operations, basically by looking at kind of sides and, of this cube. And so what's kind of interesting, okay, these are all details, but what's interesting now is that this kind of encoding encodes 3 logical qubits in one of these cubes. So it's actually called distance only 2. So it actually is error correcting code for one error, but only error detecting code for another error. But most importantly, by now just doing physical T-gates on certain qubits within this cube, you can actually implement logical CCZ gate, which is non-Clifford. And so using that and combining with these transversal CNOTs between these encoding blocks, we can now think about programming circuits, which are actually quite complex. So we'll prepare logical states plus, we'll do this CCZ and CZ within a block. We do CNOTs, by moving atoms and, entangling different blocks. And then we repeat this to kind of build more and more complex circuits. So actually, the specific circuit we'll implement will be a scrambling circuit, similar to what you've heard, Scott and others describe. But this will be not a kind of a random circuit, but this will be a circuit which will use hypercubes. So we will basically build, cubes of logical, cubes out of cubes, Basically, this is a target logical connectivity, and this basically would correspond to physical connectivity, which will be actually really quite complex here. And so it turns out that this is actually a special class of circuits which are very fast scrambling circuit, the fastest scramblers. And effectively what they do, they implement something which is called IQP circuits, which is one variety of circuit which can be used for quantum supremacy. So, okay, so, when we do it first on a small number, on 12 logical qubits, we can see immediately how error correction, in this case, error detection helps. So in this case, we have to actually throw away samples, right? Because we cannot correct arbitrary errors. So basically what is shown here, so here we still can, basically look at all strings, is still a number which can be visualized. So this shadow is basically theory, is an ideal circuit in this case. And, when you start with row, you kind of see maybe a little bit resemblance, but if you kind of turn up your error detection by post-selecting on more and more sort of perfect, stabilizers in the last round, of measurements, we see that basically this, shadow of this, ideal circuit returns. And basically what you see here also, you can look at XCB, you see it also basically, approaches, to be, quite close to Unity. So basically what we see is that this error detection really helps and helps to kind of push us towards this ideal state. So there are many different, very interesting properties of this kind of circuits. And I don't have really time to talk about it, but one of them is that these kind of error-corrected encoded circuits are very different from kind of physical circuits. In part because, for example, some gates which are easy to do, like single qubit gates for physical circuits, are very easy, but for logical circuits, arbitrary rotations are very hard. But also, this kind of results from these logical qubits experiments are actually also very different. And one key difference is that the noise in these logical circuits is really digitized. And the way how you can see it, you can basically look at these bit strings. So here again, kind of ideal data and theory, and you see it, this kind of largest strings. I don't know, it's not great here for colors, but you see that they're all kind of proportional. So there are no real random strings, but you would say, okay, so it's a dominant strings, it makes sense. But then you zoom in, on a smaller scale and zoom in more. So even at this level, which is kind of like basically an order of magnitude different, you still see a very good correspondence. And in fact, you can kind of quantify it and understand it in terms of noise really being digitized. So it's kind of basically, the errors which are, kind of coherent errors, once you do this error correction, become digital. And basically, this actually something also was noticed by Peter very early on and others, and we are now trying to really quantify it in collaboration with Robert, Nishad, and Christian. So, okay, so we went to larger and larger sizes, and the largest circuit we made was the one with 48 logical qubits. So this is a logical, each line here corresponds to a logical qubit. And in this case, by doing this kind of fully scrambling, 7-dimensional hypercubes, we still get the XCB of about 10%. So after doing, at the cost of large post-selection, of course, after doing a lot of post-selection. So basically, this is, much larger than our even best possible, physical circuit, and was sort of about maybe at least an order of magnitude larger than, sort of other physical circuits. So it would be interesting to see, for example, to compare with the new quantum experiments, how these things will compare. And so this is actually a movie showing how the circuit is made. And so basically, what you see here is that there is this hierarchical structure. We first entangle locally, then we entangle more and more globally, even more globally. Here we run out of space, then drop in a storage zone, bring some other qubits, code more and more and more and more, and then eventually we will bring all of these qubits together and entangle them. All of these things is really done in parallel, so which really kind of testifies to this efficient parallel control. So one other thing which we did is we tried to actually measure entanglement entropy in this logical circuit, and the approach here is to do 2-copy measurement. And because 2-copy measurement involves CNOT, it's a transversal operation, so it's actually easy to do. So what we do here is we prepare 2 copies, in this case is 12 logical qubit circuit, and then we do this transversal CNOT. So basically, it's a Bell measurement in this logical basis. And what we see is that in particular, when we increase this error detection, we see this this page curve, which is very characteristic, how entanglement should behave in an ideal system. And this actually basically also shows you that we actually have maximally scrambling, we prepare maximally scrambled state. So this, in some way, you can see already these logical circuits can start being useful for doing some kind of things, for example, simulations, and really exploring some interesting, actually at least kind of at the scientific level algorithms. So I will, finish maybe with just a couple of quick remarks. So since this is a session on quantum advantage, I should emphasize that in this work we intentionally did not claim quantum advantage, and in particular we build the circuit in such a way that we can basically simulate it efficiently using cleverly designed tensor networks. So in fact, the kind of algorithm we ourselves came up had a complexity of 2 to the power of n over 2, but in principle, by just doing extra level of CNOT, it becomes 2 to the n. So then there was a paper a couple of months ago from kind of IBM and INQ that found another attack, which is even more efficient here, which actually scales 2 to the n over 3. But this attack can also be broken by just moving, by just doing what's called permutation synod, by just moving qubits within this block, moving them around. So this is actually an operation which is easiest for us to do, is super high fidelity. And so in principle, it is a viable route for this random circuit. Moreover, it turns out that if you use this kind of Bell measurement, there is this kind of Bell sampling, and this is actually will be described in a paper by Dominic and others, which will appear probably next week. Another important maybe observation here is that by doing these transversal gates, we were able to get away with much fewer rounds of the error correction. And I would like to again point out that this is due to sort of naturally fault-tolerant kind of character of this transversal gate. So basically, in this case, for example, if you have an error, physical error on one of these logical qubits, this error will propagate kind of very deterministically to another physical qubit in another logical block. And you can basically account for this deterministic propagation by, decoding this kind of circuit on the hypergraph, where you don't have just edges, but you have hyper edges connecting between different qubits involved. And this actually turns out to be a very powerful approach. So, for example, in this kind of case of the GIG experiment, it's very easy to see that if you, for example, if you made an error on one of this physical qubit, in one of these blocks, how it will propagate. You can utilize this information to decode much, much better. Of course, we've done it so far on just doing one round of one gate operation and one round of error correction. So the interesting question is, how would it scale up? And actually, we have partial answers for that. So, for example, if we do the circuit with just Clifford operation with just transversal gates, and do, for example, stabilizer measurement after each round. So in this case, one can actually show that, it is actually optimal to do, in fact, in most cases, less than one round per synod. So this actually is very intriguing because usually, you need to do D rounds, for example, if you use lattice surgery. So this suggests that there might be a way to actually reduce the number of error correction rounds. So I should emphasize that this result, which is actually in this very nice paper by Mikhail, so far only is for Clifford operations. So a very intriguing question is whether this can be extended to non-Clifford operations, and in particular, in the operations which include feed-forward. So this is something that I think is a very interesting and important question, which could result in significant improvement in space-time. And then finally, I think there are some very bright prospects in terms of extending these techniques to many more, both physical and logical qubits. So, for example, based already on the stuff which I showed you, I would say the path to 100 qubit logical devices, maybe with arrays 10 to the -6, is really quite open, and I would say even in the near term. But beyond that, I think there are now a lot of the ideas in the community, both on the experiment and also on the theory side. For example, using quantum LDPC codes, how one could actually scale even further. And as a kind of an indication that there is a little bit of a transition, in the field. So here is a drawing from our lab. So it's just done by students, basically a circuit compiled by students. But now the circuit is really combined at a logical level. So they're thinking in terms of logical qubits rather than the physical qubits. And I think this actually is very exciting and really opens exciting opportunities. So I think I've used up my time. So I'd like to thank you for your attention, and also thank people whose blood and sweat resulted in this work. Thank you very much.
I'll take a few questions for Misha.
You emphasized this power of this collective operations, but eventually, before your non-Clifford operations, you will have to address qubit number 17 in that and that logical qubit to actually apply correction? Do you think this will be a practical bottleneck?
No, it is possible. It's kind of, we're already doing that already. So, but one thing to kind of keep in mind is that, for example, what for these transversal operations, a lot of that you can do in software, right? In post-processing, but of course, for things like feed forward and so on, you need to do some degree of that, and this is possible. It's just maybe reduces a little bit of parallelism, but this is. I don't see how it's important.
The limit.
Yeah. So in your locate engineering, you introduce some perturbation, and that perturbation seems to be done in the interaction picture. How to do that in practice?
So this is the key idea, is to use time reversal, right? So basically, you evolve. So the way when I I guess you're referring to this kind of creating this, multi-cycle.
Right, you have detuning delta t
Exactly.
times some n.
Exactly.
That's time independent. But then you do perturbation, that is time dependent.
Exactly. So essentially, what you do here, in this in this specific protocol, you kind of evolve, if you want, kind of back and forth, right? And this, this evolution after one cycle, results in new Hamiltonian at this stroboscopic time, where in this new Hamiltonian, the terms are basically, result of this operator spreading. And we now sort of manipulate this evolution in a way to result in exactly the operator that we would like to have in our Hamiltonian.
So basically, that interaction picture is the effective on.
Exactly. During this Fourier cycle. Exactly.
We're going to take one last question. Yeah.
Thanks for nice talk. When thinking about when thinking about reducing the resources for doing stabilizer measurement instead of doing D rounds, you can get away with doing only single round. Do you have an estimate of how much time does it take for you to do a single round on this device compared to say doing D rounds on a superconducting device?
So that's, we do have an estimate. So it is true that our kind of natural clock cycle is relatively slow, and it's, in this case, it's about 100 microseconds. Between 100, now maybe in the experiments closer to milliseconds, but let's say 100 microseconds is very realistic. But of course, if your clock cycle now includes multiple rounds, you need to multiply it by a certain number of rounds. And for that, this answer to this question, where you get away with less than D round, is very, very important. And if that is possible, that's for a big, code, D could be 30, right? So it would, if you, for example, can avoid making D rounds, then our clock cycles will be very comparable to superconducting qubits. Already as is, and hopefully this will improve.
All right, let's thank Misha again. Okay, we're going to have a panel next.